Hey folks, welcome back. In this video we're going to go over question 2 from the 2022 SQA Advanced Higher Physics exam paper. So let's get started. Question 2 says that a merry-go-round at a fun fair rotates about an axis through its centre, and you can see the two people here sitting on two horses. Part A says the merry-go-round accelerates uniformly from rest. It takes 18 seconds to reach an angular velocity of 0.52 radians per second. Part 1 says calculate the angular acceleration of the merry-go-round in this time, and you'll see there's 3 marks available. So here we want to think about an equation of angular motion. So writing down what we know from the question, we don't know the angular displacement theta. We know the initial angular velocity omega naught is 0 radians per second because we're told the merry-go-round accelerates uniformly from rest. The final angular velocity omega is equal to 0.52 radians per second, which we're told is the angular velocity reached. The angular acceleration alpha is what we're trying to find, and the time t is 18 seconds, which we're also told in the question. So I'll put a star next to alpha because that's the one we're trying to find, and we want to use an equation of angular motion here that doesn't have theta in it. So let's use the equation omega equals omega naught plus alpha t. Substituting in the numbers gives 0.52 equals 0 plus alpha times 18. So rearranging that, we have 18 alpha equals 0.52. So alpha is the same as 0.52 divided by 18. So if you put that into your calculator, you should get an answer for alpha of 0.029 radians per second squared. Part 2 says calculate the angular displacement of the merry-go-round in this time, and again we've got 3 marks available. Well, this time we're trying to find theta. As before, we have omega naught is equal to 0 radians per second, and omega is 0.52 radians per second. We have the alpha is 0.029 radians per second squared from the answer to part 1, and the time t is 18 seconds. Now we're trying to find theta here, but we can use any equation of angular motion that has theta in it. So let's use theta equals omega naught t plus a half alpha t squared. Substituting in the numbers gives 0 times 18 plus a half times 0.029 times 18 squared, and this first term will cancel to 0, so doing this in your calculator should give you an answer of 4.7 radians. Part B says 2 students X and Y ride on the merry-go-round. The students are sitting on adjacent horses as shown in figure 2a. So the direction of the merry-go-round is anti-clockwise as you can see, and we've got the 2 students there X and Y which are certain distances away from the axis of rotation in the middle. Part 1 says explain why student Y has a greater tangential velocity than student X, and it's worth 2 marks. Well, we can think about the equation relating tangential or linear velocity with angular velocity and radius or distance from the axis of rotation. So we can say that from v equals r omega, since student Y is a greater r value, i.e. they're a further distance from the axis of rotation than student X, and omega is the same for both students, i.e. the angular velocity stays the same because that's the same for all parts on the rotating merry-go-round, then we can say that the tangential velocity v must be greater for student Y, and that's because they have a greater r than x, but omega stays the same. And we can see from this equation that v and r are directly proportional. It's worth noting here that you could also answer this in terms of speed v, distance d, and time t, where if you're thinking about student Y, they're going to travel a greater distance in this circular path, and if time t stays the same for both students to rotate on the merry-go-round, then the speed v must also be greater for student Y because their distance travelled is greater, and v and d are directly proportional. Lastly, part 2 says state whether the centripetal acceleration of student Y is greater than, equal to, or less than the centripetal acceleration of student X. You must justify your answer, and you'll see it's worth 2 marks here. Well, we can say that the centripetal acceleration of student Y is greater, and to justify this you can say that from the equation AR equals R omega squared, remember that's one of our equations for centripetal or radial acceleration, since student Y is a greater distance from the axis of rotation, R will be greater for Y and omega is the same for both students. So if R is greater for student Y and omega stays the same just like before in part 1, then that means centripetal acceleration AR will be greater since AR and R are directly proportional. That's all for this video folks, thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.